It is my great pleasure to introduce to Dr. Christine Venezuela Gomez. Christine Venezuela Gomez is an accomplished physicist and researcher known for his contribution to the fields of condensed matter physics, quantum technologies, and computational physics. He earned his PhD in physics and quantum technologies from the University of Calabria, Italy in 2017. During his doctoral studies, he was awarded the prestigious Tennessee Scholarship in 2012, showcasing his exceptional dedication to the academic excellence. From 2017 to 2019, Christine held the position of researcher professor at Escuela Superior Politecnica di Chemboriza, where he played a pivotal role in teaching and disseminating knowledge in computational physics and quantum mechanics. In 2019, Christian transitioned to School of Physics and Science and Nanotechnology at Yacht Tech University, further solidifying his reputation as prominent researcher professor. Currently, he is working INFN with Professor Stefano and engaged in pioneering research in the field of plasmonic and catalysis. Christian accomplishments from his scholarship awarded PhD to his impactful research and teaching positions reflect his unwavering commitment to advancing the frontier of physics and quantum technologies. On behalf of the RIOS member, I welcome you to this webinar. Now I kindly request Dr. Christine Gomez to begin the presentation. Floor is all yours, Dr. Christine.
Today I want to talk about the Raman spectrum of graphene and graphene derivatives, okay? So the Raman spectrum is just one technique that we can use to characterize these nanomaterials, carbon materials, and other related materials using, for example, two-dimensional, three-dimensional, but all these materials working at the nanoscale level, okay? But today the focus is only graphene and graphene derivatives and how we can understand the properties of these materials by using Raman spectroscopy. This is a, maybe let me try, yeah. Okay, so this is a active collaboration where we have with the Professor Stefano Bellucci from the National Institute for Nuclear Physics in Italy, and now they're working together there. So let me show, here is just the outline of my presentation, just as a short introduction and motivation. And of course, the synthesis method to produce graphene and its derivatives, and also how we can use the Raman spectroscopy to understand all the properties involved on these synthesized materials, and of course, short conclusions. Let's start with the introduction and the motivations. So first of all, I would like to invite to everyone to imagine that you have a book, okay? So you have a book, and this complete book is your graphite. Every sheet inside of this book is graphene. Then, in other words, to contextualize here, so graphene can be extracted from graphite layer by layer. Then the graphene is a carbon structure with this pattern. So, let me activate the laser. Oh. Okay. You can see here is this my graphene. This is a carbon structure, like it's a honeycomb-like structure where the carbon atoms have a 0.1 to 42 nanometers in distance, and also the interaction or the interaction distance between planes in graphite is around the 0.33 nanometers. Okay, but this material was predicted to exist in 1859, but for the first time it was isolated in 2000 from working with the Professor Andrea Gain and the Professor and Dr. Konstantin Novoselov. They also offer a characteristic of this material from for example, from the mechanical part, the conductive part, the electrical part, optical part, and they, for all this characterization, they won the Nobel Prize in 2010. Of course, maybe the first question is how we can prepare graphene. Maybe you are thinking it's so complicated, it's so challenged, so very that we need to address before to produce a graphene in large scale. Of course, that is really true. But if you have a pencil right now, maybe you are taking some notes, you are working with graphene. Everyone with a pencil in hand also has a graphene in your hand, okay? Then all these graphene properties, yeah, so what is the meaning of these graphene properties? But before to talk about the graphene properties, we need to understand how the graphene can be found in nature. For example, graphene can be found in like a single layer graphene, so whereas graphene is a sheet, a flat sheet. Also, we can see a graphene like a carbon nanotube, or maybe a graphene like a fullerene. Of course, the Professor Andrea Gain and Dr. Konstantin Novoselov won the Nobel Prize in Physics working on single-layer graphene. Why? Because they identified different physical and chemical properties. For example, graphene shows a high temperature resistant, corrosion resistant. Also, it has it transmits heat 10 times faster than copper. Also, it has a conductivity 70 times faster than silicon, 97% transparency, and also thickness of a single layer. You know, remember, this is made of a carbon with only 0.33 nanometers. And the final and most important, or maybe attractive for several applications for graphene, it is 200 times stronger than steel. With all these properties, now graphene, more than 1 decade, so now graphene appeared with a wide range of applications. For example, conductive ink, plastic and polymers, batteries, applications for aerospace, and so on and so forth. We have just, here is a very short summary, but now every day, every week, we can identify several applications for graphene and its derivative. In our case, in our group, we are interested in electronic applications, automobile applications, and of course for water treatment, for desalinization, or maybe to treat wastewater. Okay, but before to know what is the best material for different applications, of course we need to understand from the fundamental level what is the physical, the electronic properties, and of course how is the material that we are going to synthesize using different methodologies. In this case, we need to understand just as a short summary about the different methods that we are working right now in our laboratory. Of course, this is not a description of from the chemical point of view, just as a short description about the several methods that we can use, and of course how these methods can promote different characteristics in our graphene samples. Okay, so there is a lot of techniques to produce graphene and its derivatives, but we can reduce to two very simple approaches. This is a top-down approach and the bottom-up approach. So in the top-down approach, we need a raw material. In this case, we can use the graphite. If you remember our first slides, we have our book, and the idea is to remove sheet by sheet to get the graphene. Yeah, but now also there is the scientific community is moving to another raw material, for example, to prepare graphene or graphene-like materials, for example, using biochar. In our case, just today, I want to discuss for example, what the material we can get if we use graphite, our source material. Okay, so if we move to the right side, for example, we can apply a chemical oxidation and reduction to get the graphene oxide, where the graphene sheet, the carbon atoms are covered by oxygen functional groups, high density oxygen functional groups. When we apply the chemical reduction, for example, using citric acid, ascorbic acid, or another chemical agent to reduce, what is the idea? Remove these oxygen functional groups in order to get some material. It is very similar to the single layer graphene. But also look at here. So we can see this, we can, of course, we reduce the presence of oxygen functional groups, but also we can introduce, for example, defects in the in-plane defects or at the edge. All these defects can be detected and can be understood in terms of the Raman spectroscopy. Now, coming back to the graphite, if we move to the left side, Also, we can use the liquid phase exfoliation methods where we can introduce graphite in organic solvent or water to produce few layer graphene or graphene nanoplates. Now, moving down to the bottom up approaches. So we have the most common method to prepare graphene, or the high quality graphene, a single layer graphene, in other words, is the chemical vapor deposition. But now let me repeat again. So we are, in our group, we are interested to work with the top-down approaches. Then, so there is a lot of techniques inside only the graphene oxide process for synthesizing this type of samples. For example, the common method is the Hammer's method, the improved method, and the Hammer's modified method. This is a chemical process to prepare the commonly used set to prepare graphene oxide sample and working on different applications. Okay, so this chemical process, we can identify, for example, potassium permanganate working on these three samples and also sulfuric acid. But what is the difference between the Hammer's and Hammer modified methods and compared with the improved method? And also this method was proposed in 2010 by Mark Cano. And what is the difference? Here they use the sodium nitrite in the Hammers, on the Hammer's modified method, but in the improved method they use orthophosphoric acid. And anyway, they produce, using graphite, they produce graphene oxide. In our work, we follow the similar approach to prepare graphene oxide, but we use just the potassium permanganate and also sulfuric acid, but we remove from the chemical process the sodium nitrite or orthophosphoric acid. Again, the idea is what? To get graphene oxide, and after applying, for example, citric acid, we can prepare reduced graphene oxide. As you can see, we have a lot of methods to prepare graphene oxide samples, like here, we will discuss more in detail later on, and also reduce graphene oxide samples. Another important thing that we need to take in mind is, if we are going to synthesize these materials, also we need to control several parameters during the process. For example, once we get the graphene oxide dispersion, like here, also we can't, for example, play with the temperature effect, for example, increasing the temperature from 40 centigrades to more than 100 centigrades to remove the water in just to take graphene oxide. Or also we can increase the time. What happens when we increase the times? The similar thing, once we have the graphene oxide dispersion after the reduction, also again we have a reduced graphene oxide dispersion, and we can apply the similar approach. Apply what happened with the temperature, what happened with the drying effect, etc., etc. And also all these variation in the synthesis process can affect the Raman spectra of these samples. And now let's move to the different methods now working with the liquid phase exfoliation. What is the idea? Let me repeat again. So we have, for example, polar solvents and water. So we can introduce in these solvents graphite and apply the sonication process, and these mechanical waves increase the distance between the planes and it starts to the exfoliation of graphene. And the similar thing can be done, for example, in water. But what is the problem in water? So the problem in water is the surface tension of water is higher compared with the surface tension of graphene. So if you want to match the surface tension between them, you need to reduce. How we can do that? So we can introduce graphite, water, and to stabilize and reduce the surface tensions, we can introduce the polymers or surfactants. There is another techniques to produce graphene, a few layer graphene dispersion, but remember that is different from the graphene oxides or reduced graphene oxide samples. In our case, for example, in this work, we start to we analyze more than 300 samples prepared by using back sonication in ethanol and dimethyl formamide. So to understand what is the parameters that we can control to optimize the production of few layer graphene or graphene nanoplates by using the liquid phase exfoliation processes. Then Another technique, for example, is not treat only not only sonicate graphite. Also, before the sonication, we can do an extra process. For example, in our group, we are working with the expand graphite, or also we are creating our own expanded graphite by using a hydrothermal exfoliation, which means, so we have an autoclave chamber. Inside here, we introduce graphite, water, and a surfactant. So we increase the temperature more than the 150 centigrade for more than 10 or 24 hours, and we increase the temperature, we increase the pressure, and we induce the intercalation of the surfactants. And that way we have a hydrothermal expanded graphite that, subject to a sonication process, it's easy to prepare graphene, few layer graphene dispersion in a reducing sonication time. For example, less than 1-2 hours. In order, if we don't use the hydrothermal expanded graphite, we need more than 7 hours, or some papers in the previous report, and they need to prepare a high quality graphene or a few layer graphene dispersion more than 7 days. If you take that in mind, so for a large scale production of graphene, that's not possible to take a switch on the sonicator active for the complete process. Yeah. So for that, we are trying to do something before to reduce the sonication time, and of course keeping a good quality and a high concentration of few layer graphene dispersions. And the last thing I want to comment about the synthesis methods for graphene dispersions is very simple. Maybe you can use just, for example, here is a glass with another organic solvent. We can put inside a mixer in using the zeolites. This is a macro systems. By using just the concept of the inelastic collisions, we can improve the sonication process, the exfoliation process in liquid media of graphite to prepare graphene with the high quality. There is a lot of methods, but now on this, how this method affect the graphene production, and of course, what is the material, the properties that we get after this application of this method. To answer these questions, we are going to use, of course, the Raman spectrum. But the last thing I want to comment about the the synthesis methods is about the CVD graphene, or the chemical vapor deposition process to prepare graphene. Just as a very simple illustration of how you can use how you can prepare high quality graphene. Okay, so for example, we need a metallic substrate. In general, the people work with the nickel or copper. Yeah. After add, for example, CH4 and increase the temperature, and of course the pressure, in a controlled way can remove the hydrogen atoms, keeping inside of the chamber only the carbons. And again, reducing the temperature and pressure in a controlled way, so can be grow graphene on this metallic substrate until, or the final step to get a single layer graphene with the high quality, where you can see here, this is a very nice picture or illustration of a single layer graphene on a substrate, showing the hexagon pattern of this system. Now, let's focus on the Raman spectrum for this type of systems. But here, before just, of course, there is a lot of techniques, like maybe we can start or let me first comment, we can use a morphological characterization, which is based on a scanning electron microscope or transmission electron microscope, or different spectroscopical techniques to get information about your graphene oxide samples, okay? Or graphene, or reduced graphene oxide, or few layer graphene dispersion, and so on. Okay, for example, we can use in the spectroscopical way, we can take information from IR, UV visible, elemental analysis, and of course, Raman. We can use different techniques. I'm missing also the XPS techniques. In all these combined techniques help us to characterize our material. But here just is a very simple idea to show, for example, how our samples can be observed by using, for example, morphological characterizations. Then Look at here, for example, we're using the scanning electron microscope here in the picture A and in picture B. So we have graphene oxide and reduced graphene oxide. First, after the oxidation process, with all the chemical agents commented before, so we can see a corrugated structure, so several damage in the in plate and at the edges. And after the reduction, more or less, we can identify it here by using the scanning electron microscope, a regular structure, and also the generation of different mesopores or micropores in our systems. But now using another technique, like a transmission electron microscope, we can confirm that the graphene oxide has a corrugated structure, yeah, and after the reduction process, which means that we remove the oxygen functional groups from this graphene, and we have a regular structure, a flat sheet, and this corrugated part, for example, is not observed on these type of samples. Now, if we move, for example, again using the same techniques, scanning electron microscope and a transmission electron microscope, and we want to analyze the exfoliation of a graphene, or just the liquid exfoliated graphene in DMF or ethanol. This is the very simple characteristics observed, okay? So we are observing how is the surface, how is the edge, and now here in this part we have the transmission electron microscope images. For example, now we are going to focus in the picture B, here this part, and this is graphene sonicated by 5 hours in the material format, okay? So we can see this, we can detect a lot of sheets of graphene on this part. There are sheets on this after the sonication and the format. And now, for example, if we analyze where we compare with the similar samples, but now in the ethanol and using, of course, 5 hours of sonications, also we can see a little bit sheets, semi-transparent nanosheets here. Of course, but if you compare the picture B in the picture F, of course, we can see here is a darker regions, and of course, the layers by layers, like here, is not observed when we exfoliate graphite and ethanol. So the best from this result, very simple, we can see that the best solvent to prepare graphene, at least in this result or in this our paper, so is this dimethyl formamide. In the last one, for example, for CVD graphene, we can see in the picture A, B, C, and D, how for the people, for example, works and grow graphene on hexagonal boron nitride. So now in this high resolution 10 image, the authors show us how this a perfect graphene structure with these hexagons. Look at here. So we can observe clearly the hexagons created of this on this single layer graphene sample on hexagonal boron nitride. This is the several images, but it's a little difficult to identify all the complete properties. So maybe we can see how is the morphology, how is the edge, how is the iron, maybe the thickness, but no more information about the morphological characterization. For that, we need different spectroscopic characterization, and that we are going to use here by using Raman spectroscopy. Here, of course, it's not a lecture about the Raman, how the Raman spectroscopy works, but just let me comment basic concepts about the Raman spectroscopy. Of course, look at here, we have a target molecule, and the idea is to fall down the incident lines. Okay, after the interaction of these incident photons, we can observe different physical properties, like here is anti-Stokes Raman scattering. So we have the Rayleigh scattering and Stokes Raman scattering. Then what is the difference here? Before to analyze this figure, for example, here we can see the wavelength of the scattered photon is less than to the wavelength of the incident photon. And here we have in both the wavelength of the incident of the scattered photons are equal, or in the case of the Stokes-Raman scattering, the scattered photons, the wavelength of the scattered photon is higher than the wavelength of the photon, or the incident photon. Then, now, how we can understood this in terms of the energy? Here we have, remember that, of course, if you, for example, compare the Raman spectroscopy with the UV visible spectroscopy, of course, in the UV visible spectroscopy, you are analyzing, for example, how the absorption energy affect the electronic transitions. For example, from the pi level to the pi star level, etc. Okay, but the electronic transitions, it can be understood in terms of the UV visible spectroscopy. However, by using Raman spectroscopy, we can understand or we investigate the vibrational modes or vibrational states. And now, to understand this effect, of course, now we can use the concept of energy. So, for example, in the Rayleigh scattering, as mentioned before or here, so the incident photon has the similar energy of the scattered photon, okay? Now, in the storm scattering, what happened here? So we have the incident photon has a larger energy compared with the scattered photon. And of course, we are, for example, in this illustration, we are in the first excited vibrational state. Or in the anti-stock scattering, we can see here the incident photon has a lower energy compared with the scattered photon. However, here, for this anti-stock scattering has a less intense or less energy compared when the stock with stock scatter. So the more important effect on the Raman or this on this type of system is the stock scattering. Okay, you can read more in detail, but this is a very simple explanation of description of how we can work with the Raman spectroscopy. Then let me focus on the core of this webinar. That is the Raman spectroscopy for different, or Raman spectra, sorry, for different graphene and the graphene derivatives. But before to analyze graphene, we need to understand our raw material. So this is the Raman spectrum from 1,000 centimeter power minus 1 to the 3,000 centimeter power minus 1. We have the complete spectrum. So if you have a high quality graphite, or your raw material is a high quality, you will see only the G peak, yeah, and you will see here the 2D band. Okay, the 2D band or the 2D peak. And when you apply the fitting by using, for example, Lorentzians, in general, the Lorentzian functions is widely used to fit the data in the Raman spectra. So using these Lorentzian functions, we can identify the contribution of two photons. Okay, we call for simplicity. We will discuss more in detail how this photons appears. But now here is just the 2D 1,8. This is the first band, and the second one is the 2D 2,8 band. So working on this region. But in the general, your Raman spectroscopy only will offer two peaks: the G peak here and the 2D peak on this region. So how this how we can understand this the presence of this peak. However, first please focus on this picture, very simple picture. Yeah, so this is the first is a one layer graphene, the second layer of another graphene, okay, interacting each other to create a three-dimensional structure of graphite. So inside of the plane, we have strong bonds in the layer. So it is connected with the sp2 hybridization, creating between the bond between the carbon atoms in the plane is the strong bond or sp2 hybridization. Then, when we are working here with for example, when we want to analyze the interaction, the layer by layer, so now the interaction between the layers are weak bonds. Or in other words, this type of interaction are well known as the van der Waals interactions. Yeah, so these are very simple to understand that here. Then, how this G peak appear? This G peak appears, as you can see here, in the in-plane vibrations. Due to what? The sp bonded carbon atoms. Yeah, so the GPIC give this information about the sp bond carbon atom. So if you have a narrow GPIC, so you have a good graphene. Why? Because also give information about the crystallinity. Okay, so you have a higher crystallinity if your GPIC is very narrow. If you have a broad peak, of course, the crystallinity of this system decrease. Yeah, the position of this peak is found more or less at this at this frequency. Yeah, of course, there is the application in particular for this peak is identify, of course, the presence of the carbon materials and, of course, the crystallinity of the carbon material you have. Then, now let me move to the 2D peak. In the 2D peak here, now it appears, or first, it is known as the second order D peak or G peak. And also it appears, as mentioned before, to the two-phonon lattice vibration process in graphite. But two important things can be taken as information can be extracted from this 2D peak. For example, the stacking order, that is interaction between the graphene layers in graphite, of few layer graphene, or graphene nanoplayers, etc. And also, of course, if we have a bilayer graphene, trilayer graphene, and so on. Yeah, but also the interesting thing, if we have information about the stacking, of course, about the stacking, and then for a qualitative expression, we can estimate the number of the layer by using Raman spectroscopy. So we can identify more or less what is the number of the layers on the graphene sample you prepare for the different methods you already are working right now. Okay, then, so as mentioned before, we can, for example, understand by using Raman spectroscopy the stacking, but the graphite have a lot of, not a lot, so more or less 4 configurations about the stacking. But the most traditional stacking identified in graphite is the AA stacking, where you can see this is the configuration, or the AB stacking for graphite. In particular, in our experimental part, of course, we are using our raw material with this AB stacking here in this our graphites follow this configuration, this structural configuration. But also there is another one like AAB, sorry, AB8, ABC, and another ones, another interesting graphite system. But now we are not focused on the stacking on this part, because the idea is to get, maybe it is possible, of course, to get a single layer graphene, or maybe a graphene prepared with the less than 10 layers, yeah, from graphite. Yeah. Then let me continue with the analyzing now the Raman of our graphene samples. For example, in this in this work, the authors show how they prepared by chemical vapor deposition a 3-layer graphene, 2-layer graphene, and 1-layer graphene. All this spectra is compared with the graphite spectrum. And the interesting thing here is, depending on the depending on the process you applied, for example, they identified as less intense peak, D peak here. Extra peak. Remember that we have G peak, 2D peak, and now in the case of single layer graphene, the authors identified the presence at the very small D peak. But also, for that, before I was trying to contextualize the different process in how, for example, maybe if you are using the chemical vapor deposition, but you increase the time, you increase the temperature, you increase the pressure in the different ways, of course, you can get graphene, but this graphene can be changed a lot. For example, in this another work, the author report also the presence of the production of the graphene, of single layer graphene. But if you compare this picture here of this Raman spectrum for this single layer graphene with this one here, so here we can see this is a deep peak, so intense we compare it when this is. But however, a boot process, in boot works, they use the chemical vapor deposition to prepare. But the idea is, I want to highlight how the very simple parameters, just changing one, for example, can change dramatically your graphene samples. And of course, if you want to get, for example, the people propose, if you want to identify if your graphene oxide sample, sorry, your graphene sample is high quality, they can take the ratio between the intensity of D peak over the intensity of G peak. If this ratio is equal or near zero, of course, you have a high quality graphene. If we can see this condition is observed on this here. So this is very small, goes to zero. So we have a single layer graphene of high quality. Or in this case, of course, this is a higher, of course, larger than zero. And of course, also we have a single layer graphene, but this is with the presence of this D band. Okay, if we are going to discuss. And also, if you remember, the 2D band or the 2D peak is a fingerprint to identify the staking order and also the number of the layers. So if we can take the ratio between the intensity of the 2D band over 1G band, and this number is greater than 2, you are working with a single layer graphene. So here, for example, the authors call this band as 2D peak, or the author here called this is another name for the same vibration modes, that is the G prime peak. That is, but just these two different notations, but the bands are the same thing. Okay, just remember this ratio if you are working with the Raman spectrum to identify different materials. So this is a very simple qualitative technique to identify how is your material, the number of the layers, your high quality or no quality. Then let me go back to this part. So at this part. Now, maybe the question is, okay, we know what is the G peak, we know what is the 2D peak, but what is the meaning of the D peak? So the D peak, from the theoretical concept, is related to the breathing modes of 6 atom rings and requires a defect for its activation. Yeah. So coming back, what is the meaning of this? Is in the simple words, is the presence of the D band can be attributed to the effects inducing after the preparation process. Yeah, so you can see here, this is for, let me go back again. Oh, yeah, so for example, using the chemical vapor deposition, you have an intense D band and D band. What's the meaning of the words? So here, this is a single layer of graphene with the high density of the effects, and here is a single layer of graphene, but a low density of the effects. And also, this is the position, more or less the D band is detected at 1,350 centimeters per power minus 1. And we need to give a deep discussion or a deep analysis about the Raman spectra, but at the first approximation, we can attribute the presence of the D band to the presence of effects such as vacancies, grand boundaries, or another type of defects. And we can read more details about this band. Now, let's go to analyze the Raman spectrum of exfoliated graphene. So here before to analyze the Raman spectrum in this work, we also we complete this characterization by using density functional theory computations. And the idea is, again, if you remember the different process, but if you want to exfoliate, what is the idea? Is increase the interaction distance, or increase the interaction van der Waals distance between the graphene layers to obtain graphene layers. Yeah, so we increase the distance and we obtain the graphene layers. From the sonication part, how we can do that? Of course, the mechanical waves increase the distance between graphene layers in the graphite structure and introduce the solvent molecule. That is the idea of this representation. But you note, we can remove these solvent molecules, for example, working with boiling point. Okay, for example, for the ethanol, the ethanol disappear after that, after 65, 60, 70 degree. Okay, so now this is the model we propose about the exfoliation process of graphite using two different solvents, DMF or ethanol. But the important thing here is what happened now with the Raman spectrum. And of course, if you remember, the idea is to reduce the sonication time in order to get the few layer graphene dispersion with the high quality in the high concentration. That is the goal. And all the people are continue working together with these applications, the potential application of these few layer graphene samples. But for example, if we can see, we just focus on the G-band regions. For example, after 2 hours of sonication, what happened? Of course, we can observe again the G-band and the G-band. And after the sonication, 2 hours, 5 hours, and 7 hours, independent, if we are using dimethyl formamide or ethanol, we can see the presence of the D band, of the D peak. So if you remember our previous explanations, so it's the presence of defects. But the important thing here is when we go after the 5 hours of sonications, another peak appears. That is the D prime peak. For example, here, 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 and here. This is another or extra peak. So, but this peak is also an indicative of the presence of defects induced in our exfoliation process to prepare graphene oxide dispersions. Then, okay, the D and D prime peak are connected with the defects on our graphene samples. But what type of defects? If you remember, we talk about, for example, basal defects, in-plane defects. We talk about the vacancy defect. But in this work gives light how we can identify or how we can interpret the defects induced after your exfoliation process. For example, here, if you take again the ratio of just the intensity of the D peak over the intensity of the prime peak, and you can have different numerical values. For example, if you have 3.5, you are working with edge-type defects. So you have different defects at the edges in the plane of your graphene system. And also, if you have working with the similar approach in the ratio gives the value of 7, you have the vacancy type defects. If your number in particular, if it's greater than 10, or here, like here is 13, so we have ASP3 type defects. I will try and illustrate when we will talk about the graphene oxide, what's the meaning ASP3 defects. But please take in mind, in our case, when we take this ratio, our numerical value for every sample, of course, and until say 7 hours of sonication is near to is close to the 3.5. And of course, in the type of defects we introduce in our exfoliated graphene is just the edge type defects. This is another way how you can identify or how we can interpret the Raman spectrum in the concept of these numerical values, and to write, for example, a paper or scientific communication on this characterizing your graphene samples. Now, let me focus on the 2D band for the exfoliated graphene. Before, in this work, you can see here, for example, the Raman spectrum for 1-layer graphene or single-layer graphene is the same thing, 2-layer graphene or bilayer and bulk graphite, and also the Raman spectrum for the carbon nanotubes, but it's not the focus of these explanations. Okay, but if we analyze the 1-layer graphene, maybe the question is why we didn't do any fitting on this? Because this is a very narrow peak, the 2D band. So this can be fitted just by using the 1 Lorentzian functions. If we analyze now the graphite, like in the previous in our sample, we have 2 Lorentzian functions that can be used here, can be used to fit the graphite. But if you have 2-layer graphene, tri-layer graphene, and the 7-layer graphene, you can fit your 2D band with 4 Lorentzian functions. Okay, look at here. Here the authors call like P1, P11, P22, P21. Here writing in this table, for simplicity, we identify the similar peaks in our study band regions, but we call just here to the A, to the B, C, and D. Here is the corresponding the correspondence for our work, which is another one. But most importantly here is how to connect these bands, how appears this band. To understand this part, we need to move to the electronic electronic band dispersion or the band structure of, for example, bilayer graphene. If we take the high symmetry path, for example, gamma, kappa, M, or kappa, kappa, and kappa, so we can see this is the famous Dirac cone. Of course, is not well observed the Dirac cone in bilayer graphene. However, I use this image to show how is the bands. For example, here we have in the valence bands and the conduction bands, we have the pi 1, pi 2, pi 1 star, pi 2 star, and so in the similar thing for the figure B. So, and from this picture, you can see here the different transitions. Pi 1, pi 2 star, pi 1 star, pi 2 star, pi 2, pi 1 star. So you can connect and from this part we can take, of course, we can analyze the white in this 2D band region for few layer graphene dispersions or bilayer graphene dispersions can be fitted by using 4 Lorentzian functions. That is important here. Now, but please take caution on this part. I'm not talking about that. For example, using by using the liquid exfoliation, you can get a few 2-layer graphene. No, the idea is how the structure of the 2D band in graphite change when you have pure layer graphene or exfoliated graphene. So remember, in the maybe here's okay. Okay, after I will comment again. So if you remember, the 2D band in graphite only can be fitted using 2 Lorentz functions, but now the few layer graphene, the 2D band structure, the 2D structure change, and now we can fit using 4 Lorentz functions. And this is another confirmation that we are reducing the number of the layers. Of course, we don't have a 2-layer graphene, but our graphene maybe is less than 10 layers. So we are working with few layer graphene. Now, to understand how is the graphene oxide, the Raman spectrum graphene oxide, first, I would like to discuss about this theoretical view. On this work, we use a supercell made of 8 carbon atoms and introduce the most common oxygen functional groups, which are epoxy groups and hydroxyl groups. From this theoretical point of view, we increase the number of the functional groups to understand what happened with the oxidation degree in the synthesis process. For example, if we don't have any functional group, we have the carbon-carbon bond is 1.42 angstroms, which is connected with the sp2 hybridization. But once the oxidation degree increase, or we increase the number of the functional groups independent, we have oxygen or hydroxyl groups, we can increase the distance between the carbon-carbon atoms. For example, more than 1.5 angstrom, that is a typical distance detected on diamond, for example. Yeah? And that, of course, the hybridization of the diamond is the type sp3 hybridization. Yeah. So that is, if you increase, you can move from sp2 to sp3 hybridization, introducing the oxygen functional groups. But in the real life, of course, or at least in our oxidation methods, we can reach only the maximum is just 50%. But what is the idea? So if we introduce the oxygen functional groups to exfoliate by the chemical concept our graphite in order to get graphene. Now the idea is, if I want to recover the the properties of our graphene materials, or the pristine graphene, we need to apply a reduction process. In other terms, so the oxidation moves to the sp3 hybridization, and the reduction moves from the sp3 hybridization to the sp2 hybridization. Yeah, that is the idea. So the oxidation moves to the right side, to the reduction to the left side, in order to recover the different, or modulate to different hybridization properties. And just to comment, here is the elemental analysis. What happened here, it's, for example, with any reduction process, just our pristine graphene oxide offers a 50.3% of oxygen, and similar for the carbons, okay, for example, 50-50 more or less, okay? But when we apply the reductions, so for example, as mentioned before, citric acid, hydrazine, and other chemical agent to reduce the number of the oxygen functionally induced in our graphene oxide samples, so the presence of oxygen starts to decrease. For example, this is the best one at the 1.5 hours is the best reduction process. After, for different, I don't know, maybe because it's not controlling, is not performing the controlled way, the synthesis, the reduction process, again, our material lose oxygen and functional groups, but after that take from the air again oxygen functional groups. But for example, but here I want to highlight this increase in the reduction time. We can reduce the oxygen, which means that we are removing from our graphene oxide, we are removing the oxygen functional groups to prepare reduced graphene oxide. Then, just to remember here, this is the graphene oxide, this is the graphite, the Raman spectral graphite. Now, remember, now that we have the Raman spectrum of exfoliated graphene, where extra to the G and to the peak, we have the D band and the D prime band. And now this is the Raman spectrum of graphene oxide, but it's very different. So if you see, you compare, it's very different to the previous two ones. So we have now intense D band, but it's not narrow, that is a broad band. Yeah. Also, of course, in this G band, now that we have the contribution of the G band and the D prime band. And the interesting thing is an extra band appear, that is the D star peak that we will discuss in a few seconds. But now, if we analyze the 2D band regions, look at what happened here. If we remember, we have a different structure in graphite or in the fuel layer graphene, but now here we have an extra peak here. So the D plus G peak, and if we start to fit all these peak, we can see this 2D 1A, 2D 2A, and now the extra D plus G peak bands. So represent. So we have an extra bands. For that is the importance to try to understand how these bands appear, and of course how we can modify, control, how we can, or even how we can exploit the presence of these bands for different applications. Then, now what happened here? So the previous was, if you remember, here is the Raman spectrum of graphene oxide. What happened if we increase the reduction times? So just playing with the reduction time, independent of the chemical agent used for the reduction process. So look at here, again, we have D, G, D prime peak. In all these peaks, for example, starting from 0.5 hours of reduction to 24 hours of reduction. Then what happened here? We identified in the previous, in the graphene oxide, we identified the D star, but once the reduction process starts, an extra band starts to appear. That is the D star band. So appears an extra band. Okay, to understand how these bands appears, we can understand in terms of the amorphous carbons. Yeah, but remember that we are not working with the amorphous carbon. We are using we are using the graphite as a source material with a high quality, and these interesting bands start to appear. But please, just a parenthesis on this part. And for the D star band is observing in amorphous carbons due to the presence of finite size graphite crystals CH vibrations in hydrogenated carbons or hopping light effects. And also, the presence of the D star band is related to the sp3 diamond line in the solar amorphous carbons. Of course, we are not working with the amorphous carbons, but we have our graphene oxide sample. Depending how the oxidation is done and how the reduction is, of course, done, so we have these characteristics. So we can modulate, and of course, maybe some of you can identify different applications for this type of system with these different effects. Then, but look at what happened here. The G band represented by the in the orange color and the D prime represented in the blue color, in terms of the intensity, remains at the similar position, similar intensity. Sorry, but what happened with the with the D star or the D star is star star? So once the reduction process begins and continues in time. So what happened here? Also, the intensity of these peaks start to increase. Look here, it start to increase the intensity for D star and D star star. And this is not trivial. So the intensity increase is because a high density of something is inside of our material. Then, now, let me focus. We are just near the end of this presentation, but please just give me a few minutes to finish. This is let me focus now in the in the band 2D band region. If you remember, in the graphene oxide we have the 2D band, 1A, 2D band, 2D, 2.8, and the extra peak is the D plus G. So, and again, when we start with the reduction process, the interesting thing is, for example, compared with this 0.5 hours of reductions, and now when we have the after the reduction of after 24 hours, look at here, the intensity of this 2D to 8 band increase and reduce the intensity of 2D 1.8. Of course, in this material, for example, it is so complicated to remove the contribution of the D plus G. For a moment, please forget this contribution and focus on the magenta line and the green line. And we compare, maybe it's not good because here is, of course, but the idea, please don't follow the color, the color line, just follow the notations. What happened here? So if we compare, look at here in this part, the 2D band for graphite or our starting raw material. So this is 2D band increases a high intense, and now the 2D 1A decreasing intensity. And that is here, if we observe after 24 hours of reduction, we can compare both the Raman spectrum of this 2D band, and the main conclusion is we are trying to recover the graphitic-like structure. That's very good because we have a corrugated structure. And after the reduction time, we are removing the oxygen functional groups, which means that we are trying to recover, of course, the intrinsic properties or the properties of pristine graphene. But of course, it's not possible to get a single layer graphene by using the chemical or the reduction process. So, but if you remember in the previous slide, we talk about the 2D band, give information about the sticking and of course about the number of the layers. Then here we can see that we are recovering the graphitic-like structure, or in other words, we are recovering a layered structure. We are trying to recover a layered structure after the reduction process. And now, the interesting here is, of course, in amorphous carbons, we mentioned before that for example, the D band appears due to, for example, the finite size of graphite crystals or different vibrations. And of course, the D star band appears due to the sp3 diamond length, etc. But when you observe in the Raman spectrum the presence of D star band plus the presence of D plus G band. So you are talking about only about the effects on your graphene oxide sample of your reduced graphene oxide sample. It's not really connect with all these other contributions. This is because, of course, we are not hydrogenating our graphene oxide. So it's only connected with the effect. What type of defects that previous comment before? So, for example, in-plane defects, edge defects, vacancy defects, and so on and so forth. So the presence of these give information about the defects on your samples. And if we want to analyze here, for example, here, what happened when the 1D18 and 2D18 and 2D28. So in both cases, in black color and, please compare the black color and the red color lines. So it start to decrease and also decrease. That's we observe. Yeah, so we can observe like the similar behavior for the graphite structure, but in the contribution in the 2D2A band here, this is represented in blue color, it starts to increase. Yeah, so it starts to increase. For example, here is a lower intensity, increase the intensity, more intensity in here. Of course, maybe our hypothesis even increase, for example, more, maybe for 84 hours, 7 days, I don't know. We didn't try to extending the more reduction time to it is possible to get something this structure. The idea, in theory, we expect increasing this, increasing the reduction time, we will observe something like this. Okay, but in this result show that is not really possible. Maybe, for example, for the 2A, yeah, representing this blue color, you can see here is the maximum. Okay, maybe we can increase. So this is a saturation point. Of course, maybe a little can be increased a little, but it's not possible completely reproduce or get the graphite-like structure. But this the notation for this part. Okay, for graphene oxide samples and reduced graphene oxide samples. To finish our this webinar, of course, we can use the Raman spectroscopy for characterizing graphene and graphene derivative. Why? Because it's not a destructive technique, and also it's a high sensitive technique. For that, I mentioned before in the previous slide how the G peak is affected, how the 2D peak is affected, and how appears extra peak. Of course, less intense, but it starts to appear depending on how you control the synthesis process. Independent, you are working in the top-down approach, even if you are working in the bottom-up approaches. And of course, information about what? So we can use, for example, to obtain information about the structural information, number of the layers, quality and disorder, strain and strain analysis, doping effects, its properties, chemical modification that can be introduced, and substrate interactions is taken order. Okay, and also the conclusion from this webinar, of course, is the difference. The important thing, I don't want to read the conclusions, but the important thing here is to highlight how is the Raman spectrum of graphite here in this part, how is the Raman spectrum of exfoliated graphene, and how is the Raman spectrum of a graphene oxide or reduced graphene oxide. Then for that, of course, we have a lot of synthesis methods to prepare graphene and its derivative, but also we need a different technique to characterize what type of graphene we are producing. Until now, we don't have a standardized process, a standard process or a ISO norm to prepare graphene oxide. For that, this is a continued line of research, how to prepare graphene, and of course, the prepared graphene, how can be explored, how we can use for different applications. and depending on the synthesis process we have. Finally, thanks again to the kind invitation to be part of this virtual international conference. Also thanks to the complete organizing committee, and also I will give thanks to my collaborators, and of course this is our group in Italy. In particular, here is the Professor Stefano Bellucci. Here, maybe if someone needs some extra information, maybe some collaboration, or maybe you want to contact to ask about these slides, please, you can contact here. We have our emails. And also I would like to thanks to our group in Ecuador. This is in Universidad Técnica Particular de Loja, where they are working in all these methods I mentioned before to synthesize it. They are working together with us. We are working here in Italy with for example, the graphene nanoplates obtained by expanded graphite and using the microwave process. But this is another history that maybe in the future we can discuss. And of course, we have an active collaboration with another professors from the University of Calabria, where we are trying to use all these material for pollutant removal, to treat mercury, to treat different, heavy metal, in general, heavy metals and dyes. So we are trying to use, in particular, graphene oxide and reduced graphene oxide. We are trying to use this material, exploring all these properties, all these effects, and so to obtain the best performance when we are trying to treat wastewater or removing pollutants or dyes from water. Okay, thank you so much again for the kind invitation.